This is Kieran Vernier, Vertical Scaling Analyst for the Ministry of Omniplex Resources. A new machine was assigned to our department for evaluation, and the only available real estate for installation was inside a water treatment facility. So this is where that assignment begins. I ordered and installed a new mobile platform for the unit, which will hopefully be useful for the ministry on both this and future endeavors. The platform was tested with weights and temporary scaffolding to ensure structural rigidity. The units we received are the Halot-X1 and the UW03 from Creality. The reason we had to use this particular facility is external venting, which is unavailable in the other work areas around us. This process must follow proper PPE protocol and safety standards per Dominion regulation. Although I am not unfamiliar with the concept of masked stereolithography, I had never handled this process personally before. This machine uses a leveling-free setup, which seems accurate because I did nothing special and the build plate worked on the first use. Right away, my favorite feature is the twist-release build plate, which makes part removal very easy. And the UW03 washing station makes it straightforward to remove excess material from the printed parts. Because of the build plate design, there is a technical note to make the first layers thicker than you might expect, and I don't fully understand the reason yet because the software handled the process for me without issue. The UW03 station is also capable of carrying the parts into their final form, and the demo piece included with the machines seems to have worked out well enough. I wanted to run an actual test using my own ministry supplies, and again, I really like the design of the twist-release build plate. Creality also included the AFU module, which handles resin feed and recovery for a more automated workflow. The build plate is a little harder to clean because of the moving parts, so be careful and use a non-metallic, non-damaging tool whenever possible. I should clarify, this report is not a tutorial for anything you are about to see. If you need specific instructions, I am not the person to ask about this machine. I am simply reporting my perspective, and my perspective is that this 16K resolution is actually pretty incredible. I'm very happy with these results, and any defects or problems that you can see on the parts themselves, I've researched and determined to be almost entirely user error. This is a very good baseline for precision analysis, and I think the most interesting way to analyze it is to pit this manufacturing process against a manual process and see how difficult it really is. Comparing with old reports, you can see that the new process is much more precise than previous ministry attempts. Unfortunately, there was a problem with the facility infrastructure, which should have been a sign of things to come. After receiving the green light to move forward with Project Micron, I began by sourcing parts. I requested the smallest, highest fidelity components and precise electronics available within our stockpile in order to test this project. This may not have been the most efficient route, but the focus here is precision and accuracy, and we will need the most accurate structures possible in order to compete against the Halot-X1. I figured the easiest place to start would be the head of the unit because it is the simplest shape of all the subassemblies. Although the ultrasonic cutter is useful, it is not accurate enough for most of this build and was only used for rough sourcing. The printed baselines were used as references to compare against and evaluate accuracy throughout the build. I was able to use standard tools like the grinder to clean up roughly cut parts and begin welding a couple of these simple pieces together. A precision vise helps a lot with this process and is used quite a bit throughout the entire build. Some accurate cuts still need to be made, which, although potentially risky, were still straightforward. If you need parts like this and you don't have the time to do what I'm doing, you can always reach out to the Dominion's partner PCBWay. PCBWay provides advanced 3D printing, PCB prototyping, and full-scale manufacturing, making it easy to create intricate custom work. They offer a wide selection of both plastic and metal materials. As mentioned, I am not unfamiliar with stereolithography and have personally utilized their UTR 3000 resin. Next, I decided to start on the chassis. The body uses a strong material casing that was previously discarded. This thicker material is necessary to protect torso components. This design follows the Dominion Variance Doctrine, which states that all combat machines must be uniquely designed and fabricated, ensuring no two units share identical configurations, so hostile forces cannot predict, replicate, or counter Dominion technology through pattern analysis. Since this chassis design has not been used on any frontline units in the past, it was deemed acceptable. There is no formal blueprint, which helps maximize variance from other combat units. Only an understanding of the iterative engineering process is necessary to achieve functionality. For the torso-to-hip connection, I built a simple spinal waist subassembly. Like the rest of the joints on this unit, the connection uses magnetic latches. It's a very resource-intensive approach, but I do not want to compromise on articulation this early in the process. I installed a central hex core in the torso, creating a sheared anchor point between the head latch interface and this first version of the waist assembly. After a quick test fit, I added a small amount of armor and prepared the hip joints for leg attachment. For now, I also reused the same joint format on the shoulders so I could evaluate arm attachment before committing to a final design. Because the shoulder sockets were available, I decided to begin working on the upper arms. They were carefully modified to fit on the same magnetic latches used throughout the rest of the build, then attached to the first version of the shoulders. Unfortunately, the bushings I had available for the elbow joints and other future joints were much too large for this particular project. I had to use a precision lathe to machine these bushings down to smaller diameter acceptable for Project Micron. After polishing the parts and confirming they were identical in size, I checked all the pieces and spares to ensure they met acceptable quality standards. They were then connected with additional magnetic latches, and precision building was used to ensure that the latches would not fall out of their casings. The upper arm was then welded to its elbow housing. Having the legs built, even as a static frame, would be ideal for evaluating the overall proportions of the unit, so I began working on them next. Immediately, I noticed that a compound angle in the hip joint would make thigh attachment much harder. Using simple holding techniques, I was able to align the thighs with the lower legs to create a basic structure that Micron could stand on. This was the first real look at proportion and comparison against the Halot-X1 output. At this point, I had the option to work on the lower arms or continue with the legs, and because I dislike working with static ankles, I stayed with the legs. I developed a new precision ball joint concept for the feet so Micron could stand on uneven surfaces and shift body weight more effectively compared with previous ministry attempts, at least at this level of precision. I took an extra spare of the calf design and cut it to fit a magnetic latch for the ankle assembly. During this process, I made an important discovery. By using a rubber seal shrunk with heat as an interface for the ball joints, friction could be managed more easily and actuated more precisely. This completed the first version of the foot. While I was already working on the calf, I also attached the knee joints and reused the thigh from the static test to keep moving forward. This was reinforced with an extra pushing on the interior of the leg to provide more surface area for the joint to support the weight of the machine. This joint broke more times than I can remember, and I would recommend finding a better assembly method. There was only one incomplete component left at this stage, which was the lower arms. In general, I follow an iterative process and move back and forth across the machine design, gradually improving all areas so that the overall quality stays consistent. But first, every component has to exist. To begin, I built the lower arm attachment to the elbow so I could develop a hand using an even smaller and more precise ball joint. I checked our source of round stock scraps and found 450 micron linkage material for use with the fingers. Each finger is carefully shaped and installed one at a time. The first hand design was fairly straightforward, based on previous ministry attempts at small robotic hands, but I disliked how bulky the overall result was, and I do not think it would have performed well in the field. I then built a smaller and flatter version, but compared with the Halot-X1 baseline, it was clear the design was still too wide. I made a third version that was even sleeker and much more refined. I was much happier with this design. It compared well against the Halot-X1, and I decided to move forward with the installation. The wrists used additional magnetic latches, and I also tried to apply the same rubber seal process, which caused some headaches at this scale. After a brief interruption, I was very happy to recover the part I had lost and continue moving forward. I realized that instead of trying to cut the rubber seal to an exact dimension, it was better to undersize it so it could be shifted and seated into the correct position during assembly. This was then attached to the wrist with acrylic, and these test shots show the full articulation of the arms. Because of what I learned about the rubber seals, I wanted to rebuild all of the magnetic joints that were already installed so they would perform much better. This ended up being a very good decision overall, and I had to get creative with a few attachments where the new process did not apply as cleanly. Here you can see a before and after comparison of the hip movement in the leg without a rubber seal, and adding a rubber seal to the joint shows how much stiffer the motion becomes, which is far better for controlled mobility. I also added an extra seal within the waist, mostly because I was already applying them everywhere else. I was still not very happy with the ankle joints because I had not used the undersizing method. The seal dimensions were slightly off, so I tried adding an extra magnetic latch to the sole of the foot, which, unfortunately, did not seem to improve much. The hips were driving me insane because of their compound angles, so I removed the hip joints and added plate material to straighten the connection. This helped dramatically and made the hips much straighter and more horizontal. I unfortunately had to remove the upper thigh connections in order to rebuild them and fit this new hip joint. I took the opportunity to install the rubber seal there as well, and the machine was much easier to actuate once everything was properly put together. Now that the initial pass for Project Micron was complete, we still needed to see how viable it was to fabricate something as straightforward as a submachine gun for use with this unit. The parts were built using standard large-scale practices, including right angles and jigs to align components. Using several pieces of sheet material, I was able to carefully machine the upper receiver and add panel separations and supporting subcomponents. The trigger guard was added along with various latches connecting to the lower receiver, and release buttons and holding fixtures were also installed. The barrel was shrouded with a heat guard and attached to the front of the upper receiver, while a lower foregrip was attached beneath it. A protective wireframe was placed around the barrel to prevent impact with nearby surfaces, and an extra magnetic latch was installed inside the handle specifically for use with the Micron unit. This would not affect human operation. After rebuilding the shoulders with a better ball joint design and a new rubber seal, I continued with the arms, beginning with a protective frame for the outside of the forearm. My first attempt used metal components and a truss-like design to protect the assembly, but it took a very long time and it failed dramatically. Parts at this scale are extremely difficult to hold accurately while still being able to release them, and I tried many different attempts and materials trying to make the process work. I quickly learned that round stock was very difficult to work with, and flattened stock was a much better use of time. This let me miter the joints and ensure the parts were fitted correctly. The single component across the entirety of Project Micron was a dramatic turning point for me, as I realized the extent of my ability to produce precision parts at this scale. I did not look forward to combining such small parts together again, so even though 4 panels were intended, I could only muster the effort to build 2. Although the Halot-X1 is not able to use recycled parts as I can, I am not able to meet the same precision that the machine is capable of. There really was no chance at all. Although I can clearly handle manipulation of parts of this scale, the manufacturing of such components is beyond me, and perhaps an engineer more capable than I would be able to pull this off in a timely manner. After such an arduous set of trials, I needed an easier win, so I decided to continue working on the legs. Being able to use straight stock material along with pre-built pistons was much easier than fabricating so many metal components directly. I was able to make the calf pistons manually, which I have done before, and it felt easy by comparison to what I had just gone through with the arms. A small stability sensor was attached to the top of the waist, mimicking the design showcased in the Arbiter broadcast about a year ago. A simple armor plating was made to protect many of the functional systems that had just been installed. There was one particular component I like to disassemble for sourcing flat metal caps, which make excellent joint covers and help protect them from dust and debris. A stopper was added within the knee joint to prevent overextension. Rather than following strict designs, I try to keep proportions in mind, and I really did not like how wide the shoulders were. They were also limited in mobility, so I decided to rebuild them for a third time. This new design uses the same ball joint concept, but with less casing material, which allows much more movement and a cleaner upward range. Here is another example of how unstable unsealed arms can be. Small armor panels, similar to those on the legs, were cut and attached to protect this newly exposed joint. Notches had to be cleared for piston movement, and an outer panel was added for full protection. Precision fencing was attached, and the wrist mechanics were wired into the rest of the arm. Additional conduits were also attached to the upper arm, and with one final plate, the arm assemblies were finished. I have lost count of the rebuilds at this point, but I really do not like single-piece feet. It is simple enough to separate the heel from the pad, and doing so will give the unit much better mobility in the field. Similar to the shoulders, I did not like how wide the hips were, and they were still sitting at a slight angle, which made walking routines very difficult. A simple solution might have been to use a ball socket joint, but that also would have made the pelvis wider. I only wanted to tweak the hips, but it quickly fell out of control and became a full rebuild of the waist. It may have been easier to restart completely, but I wanted to preserve as much of the existing work as possible, and I managed to keep part of the original design. With everything back in place, I was able to install some electronics and finalize the waist assembly. By this point, the Halot-X1 could have printed an entire army of units, and for repeatable production, it is simply faster and more consistent. But while I am fitting these leg armor plates by hand, it is also a good reminder of the trade-off. That speed comes with fresh material, constant energy consumption, ventilation restrictions, additional cleaning materials, PPE for personnel, and post-processing with careful operation of sensitive machinery. What I am doing here is slow and probably very inefficient for this scale, but there is still real value in manual fabrication, especially when recycled materials can be adapted into one-off components that would otherwise be discarded. Manual fabrication preserves adaptability, while the Halot-X1 excels at repeatable precision, and I believe both have a place in the ministry's workflow. I will be noting this in my report to leadership. The last refinements focused on chassis details, including fine electronics and venting within the head assembly. I decided to add shoulder pads to help protect the shoulder joints, and these armor plates worked very well with the current design. Additional venting was bolted into the back of the unit, and small exhaust components were added to route heat away from rear power systems. A few electronic modules were installed, followed by conduit and wire bracing to connect and reinforce the assembly. The armor panels worked so well that I continued the same design language on the front of the chassis. To better protect several joints, I was also able to recover small gaskets from spare pistons and repurpose them as protective seals. With the main mechanical systems completed, the only remaining step was tying the front plate into the shoulders for added strength. Then attaching the last power components on the rear assembly. After each major addition, I checked the head and waist clearance to confirm nothing interfered with movement, and Project Micron finally appeared complete. All that remained was to assemble the full set of 17 components and verify that they functioned together. It was a long process, but I'm very happy with what can be achieved at an absurdly precise scale through manual fabrication, especially in comparison to what the machines are capable of. I appreciate both results, and I'll be making recommendations to the ministry on the most effective use cases for each process. The build was finished, but the project was not. Even after integrating this much precision into the assembly, applying protective coatings and the paint to the final design takes just as much care as any previous step. As always, the process begins with cleaning and preparing the parts for finishing, and nothing new was attempted here. I followed the same coating workflow documented on the Scarab broadcast. I made sure to lay down a tarp to help with cleanup and protect the facility. The procedure used here is standard in many Omniplex workshops, and no special chemicals or materials were required. Hopefully, the following visuals will be fairly self-explanatory. The required Dominion insignia took a surprising amount of effort to place correctly on Micron's shoulder, and the decal colors were too faded, so I manually corrected them to restore saturation and legibility. With the markings complete, Micron was ready for field evaluation. Preliminary results suggest there is still room for improvement, but the unit performs adequately for its intended role. As for the question of manual versus machine, this build made that trade-off much clearer. Some components at the scale are so fine that I do not believe I could reproduce them manually with the same consistency, and in those cases the machine is clearly the better fabrication tool. The Halot-X1 was never intended to replace current processes, but to serve as an additional tool, used like a scalpel for precise manufacturing tasks.
Thank you for making time to engage with this broadcast. Your attention supports the mission of the Royal Archive. Additional gratitude is extended to Royal Archive benefactors, whose contributions sustain the continued recovery and review of critical records. Full access to the Archive Discord is available for $3. Submit recommendations or concerns below. All entries are subject to review by the Royal Technocratic Dominion. This transmission is now concluded. Until next time, goodbye.